Hi all, and welcome to the Medical AI Lab talk series. I'm delighted that today we have Rayan Krishnan presenting VOS, Learn What You Don't Know by Virtual Outlier Synthesis. Rayan, looking forward to your talk. Take it away.
Thanks, Pranav. I hope to give a presentation on VOS. I've been with the lab for a little over a year. Please, let me know if you have questions in the chat, and I'll try and address them into the talk. Okay, so first, let's maybe introduce this problem of out of distribution samples in image classification and object detection. So the paper has this line that neural nets produce high posterior probability for out of distribution test reports. And you can see why this may be an issue in cases like the one they illustrate in the paper with self-driving cars, where you could have an image and there's not a lot of moose, or what's the plural for moose? Meese, something like that. Mooses, you don't have a lot of mooses in your training data set. And so when you're presented with this image, the detection algorithm will say with high confidence that it's a pedestrian because it's out of distribution. And so they present this as an issue and say that we need to be able to correctly identify when we have data that is unknown, it's actually out of distribution. So existing methods, they kind of, it's a bit of a confusing graph. This is trying to say that we're clustering data by in distribution and out of distribution. And so our clusters are kind of on these boundaries of in and out of distribution, whereas their method, it effectively can like cluster and say when they're in distribution and out of distribution, and hopefully mitigate this problem. Oh, full of moose is moose. Okay, good to know. It's like, it's not goose and geese, moose and moose. So what are some of the existing methods in this problem space? Well, we can make use of auxiliary data sets. This seems like the most straightforward. So we have in-distribution data, and then we explicitly say that we have out-of-distribution data, and that's used to try and measure and evaluate how well the model is doing, or potentially perform another round of training to say that it can adapt to this out-of-distribution data. We could also use GANs, but the paper repeatedly points out that this requires trying to synthesize images in the high dimensional pixel space. So hopefully we can do something similar or something more simple that will just give us better confidence scores. And that's how this paper progresses. So the idea that they present, VOS, has two main parts. The first part is in generating outliers, and the second part is in adding a loss term to try and predict whether it's out of or in distribution. So you can see here we have, so I'm just trying to shift around the Zoom window. We have an input and the backbone network, which will produce some kind of hidden representation. And then we plot this in this space and cluster around different classes. And now we're trying to create a threshold between what is considered in distribution and in a class, and samples that are out of distribution or like in between classes. And then we can sample some of these data points that are on the threshold or outside of the threshold of a class, and then present those to the network and train a loss function. So we'll continue to explore this loss uncertainty function and how these points are sampled. So first, for the sampling procedure, they have this method of empirically constructing these multivariate distributions for each class. So for those who are unfamiliar, this is just like a straightforward mean across the hidden representation for each of these images. And this is a covariate matrix for each of the across these classes for these distributions. And so you can imagine we have like a plot like this, and we have these nicely colored classes, but these points, we have other points that are sort of in between the classes in their representation. And so now we try and look at this distribution and select some points based on this multivariate probability distribution. This is just the straightforward PDF function for a multivariate distribution. And so now we say across these classes, we say we would like something with probability less than epsilon. And so the probability they belong to any classes is smaller than this epsilon threshold. And then we select some VK from this distribution. VK being like one of those like challenging examples. Okay, so that was just the sampling methodology. They also have this loss function. So I'm going to try and give kind of the story behind how they came up with this loss function. First, they say that the log can be computationally intractable. And this is particularly because if we're trying to measure log probability of outside versus in distribution, we have to effectively estimate the entire density function. And so they're saying, inspired on this previous paper by Liu in 2020, we can actually instead just estimate this with the log partition function. So that is like, if you look at the bottom left, this is like a classic softmax. But on the right, we can actually use a variation of this, which just considers basically the denominator, and it should be proportional by some kind of not measured coefficient, proportional. So they use this log partition instead, and the negative log partition is free energy. Also has some prior work in the out of distribution literature. So now using this energy, they say that in distribution points should have negative energy and out of distribution positive energy. So you see the V points are when they're greater than 0, then this indicator function will be 1. Meanwhile, for the regular X points, when their energy is less than or equal to 0, the indicator function will be 1. Okay, so that's like the simple loss uncertainty using just for image classification, right? So we just have like a single label. There aren't any bounding boxes or anything like that. Now they say that 0 to 1 loss is intractable, so they use the binary sigmoid instead. So it's the same equation, except now we have a binary sigmoid, and we have this parameter theta that will actually will be trained. Theta is just controlling the slope of the sigmoid. Okay, and the main point of this is that free energy does not require density estimation like softmax, and so instead we can just try and do this boundary or like classification task of saying, is this in distribution or out of distribution, and not like where is this on the PDF function. Okay, and then slightly continued, we can adapt this for object detection, where we have this learnable class weight parameter W. And they talk about this in the ablations of the importance of using this class weight parameter. So then now adding this to our object detection overall loss, we have like our location and class loss, and then we have the loss uncertainty, which we just talked about, and it's weighted by this parameter beta. Okay, then at inference time, we can make use of this same energy measurement to determine like the uncertainty, whether or not we're in or out of distribution. So we have this, this is how we can estimate the probability that a given bounding box and, a given image is either in or out of distribution. And then using this probability, we can say whether or not it's below this gamma parameter. In the paper, they suggest they have gamma set to 90.95. So essentially saying that 95% of the data is expected to be in distribution, whereas 5% will likely be classified as out of distribution. Okay. Then evaluating some experimental results. This is like the big table of their paper, and maybe I'll give it a few seconds. The bold points are the ones where they have best performance. Okay, so effectively worth pointing out that they're able to get these like best case performances with one of their two networks. So showing that they're really doing a good job of like lowering false positives and having high AUROC. They also actually, interestingly, they evaluate against methods that make use of auxiliary data sets, but they point out that this is like kind of the opposite of what they're trying to do, right? Auxiliary data sets are difficult to collect, and you have to make sure that they don't have any overlapping regions with in-distribution data sets. So it's not actually the same problem space, but they still have comparable performance to those methods. So the previous like auxiliary data set method had like 90% AURC, whereas their method had like 88%. So it's within like kind of some kind of acceptable range and it's pretty surprising that they're able to get that close without using additional data. Okay, and then now looking at some of the ablations. So there's these 3 ablations that they have for synthesis techniques. The first one is using the pixel space rather than the embedding space. So we saw that before they have these distributions that are like set up on the like the hidden representation space for an image, as opposed to the pixels themselves to make these clusters. So then they try doing image synthesis with at the pixel space using, again, mix-up methods. Then they also try adding noise as an outlier. And then finally, they generate negative proposals using this method from last year. Essentially, they find in the same thing that you know, some of these methods work, but of course there's our ideal. I thought actually some of these methods were interesting. Maybe we can also consider in the lab later trying these things. I for instance had like I've tried some you know, adding noise as a synthetic perturbation for creating out of distribution data sets, and so it looks like it's not a bad idea, but obviously theirs is like a much better approach. Okay, and then they also have some ablations for the loss function. So the 3 things that they try are using a hinged loss regularization technique, and then using a constant weight vector rather than a learned weight vector for the loss function for object detection. And then they try adding virtual outliers as like a K+1 class that can be learned, as opposed to just doing it as like kind of a classification. And again, like the method, the VOS method, which I presented, does better than those other ablations. Okay, and then I should briefly give a conclusion. So this, you know, seems to, at least from this one paper, it seems to really address this problem of out of distribution confidence for object detection, and does this in a very general way so that we could apply this to different architectures and domains, and also do it without collecting additional data. So just make use of what existing data we have, but do the smart approach with an energy-based loss function that will create, you know, effectively calibrated intervals. I think to me, this really illustrates the importance of having good calibration in the first place. Like it seems like the takeaway of this paper is if you have good calibration in distribution, then you can have more reliable confidence predictions for out of distribution data as well, right? Because they're effectively just sampling points again from within distribution, just on the fringes of those class boundaries. Yeah, that's the presentation. Thanks for listening. I will, I guess, take additional questions and lead discussion after.
Great, thanks, Ryan.